So we want to consider now integrals where we have products of powers of secant and tangent. Um, the rules for doing these integrals are going to take into account whether the powers are even or odd, very similarly to how we did with sine and cosine. The rules are just a little bit more complicated. The reason for that, of course, is that the derivative of sine is cosine and the derivative of cosine is negative sine. So there's this kind of reciprocating relationship between sine and cosine. Secants and tangents don't work quite as nicely because the derivative of tangent is secant squared and the derivative of secant is secant tangent. So you don't have this kind of reciprocating relationship, and the rules are a little bit more complicated, but not much. So in the case where what this demonstrates is the case where tangent is odd and the power of tangent is odd and the power of secant is positive. So in this case, what you want to do is you want to peel off one factor of secant tangent. In other words, I'm trying to imagine what I want the derivative to be when I do u substitution. That's what it is. And in this case, you'll see why in a minute, but I want du to be equal to secant x tangent x dx. So let me just demonstrate it and you'll see why that works. So here I have secant cubed x tangent squared x secant x tangent x dx. So I've just peeled off a power of secant, you have one factor of secant tangent and left everything else intact. So now what I want to do is you can see that this is the term that's going to become du. So if that's going to be du, then I want u to be secant. So I want to rewrite everything else in terms of secant. So let's rewrite it this way. Let's write secant cubed x, and then I have tan squared x can be rewritten as secant squared x minus 1. That's one of those identities that you just have to know in order to do this course. So now I can write u is equal to secant x, du is equal to secant x, tangent x dx, and this now becomes the integral of u cubed u squared minus 1 du, where here I've got the du, here I have u squared minus 1, and here I have u cubed. So this now becomes the integral of u to the fifth minus u cubed du, which is u to the sixth over 6 minus u to the fourth over 4. That comes out to, since u is equal to secant x, that becomes secant to the sixth x over 6 minus secant to the fourth x over 4. And the hardest part of the problem is the plus c. So we now come to a second type of rule where the power of secant is even. So in this case, what we're going to want to do is peel off one factor of secant squared. Again, I'll show you why that works. So this becomes integral of secant squared x tan to the fourth x secant squared x dx. You might be able to guess that the nice thing here is that this is going to become du, because we know that way I can choose u to be tan x, because secant squared is just the derivative of tangent. So I'm going to want to rewrite everything in terms of tangent. What I want you to do is ponder for a minute why this even and odd issue matters so much. Notice that when I started with an even power of secant, when I took out a factor of secant squared, I was able to be left over with another even power of secant. And as long as I have an even power of secant, I'm able to use the rule that tan squared x is equal to secant squared x minus 1 to rewrite everything in terms of tangent. So that's actually, I can rewrite this in the better form. That's going to be secant squared x equals tan squared x plus 1, because that's the form in which I have to use it. So that would be very difficult to do. In other words, if I had secant cubed, then it wouldn't have such an easy time using that identity. If I had secant to the fourth, it would be a little bit more complicated, but I could still write secant to the fourth as secant squared squared. So as long as the power of secant, if the remaining power of secant is even, I can use this rule. That's why this rule has to have an even power of secant. So let's go back and do that replacement. This is going to be the integral of secant squared becomes tan squared x plus 1 tan to the fourth x secant squared x dx. So now I'm going to write u equals tangent of x du equals secant squared x dx. So this now becomes the integral of u squared plus 1 plus, not plus, times u to the fourth du. So once again, this is our du, this is u to the fourth, and this is u squared plus 1. So now I can write, this is the integral of u to the sixth plus u to the fourth du, and that comes out to u to the seventh over 7 plus u to the fifth over 5, which gives us tan to the seventh x over 7 plus tan to the fifth x over 5 plus c. As we just went over, the reason that you need the power of secant to be even in order to use this technique is that when you take out a sine squared, you need the remaining power of secant to also be even, so that you can use this identity to convert the secant into tangent. Let's go back for a minute. That sort of explains why you need the power of tangent to be odd in this case. The reason is that in this case you're going to use the identity tan squared x equals secant squared x minus 1. So you're going to need the resulting power of tangent to be even in order to be able to use that identity. Well, that's only going to happen if the power of tangent started out as odd. So the question is, what happens if you don't have either? In other words, you have an even power of tangent and an odd power of secant, or maybe you just have no power of tangent at all. That brings us to this type of problem, where here I don't have either. I have an odd power of secant and an even power of tangent because I have tangent to the zero. So the technique here is going to be to use integration by parts. I want to use this to demonstrate another principle, which is sometimes it is actually useful to be able to write to write the integral of 1 power of a trig function in terms of a lower power of the same function. So what we want to do is we want to write secant cubed x we want to write the integral of secant cubed x in terms of the integral of secant x. So this is how you're going to do that. What we're going to do is we're going to use integration by parts. And the choice here, remember, I have to choose u and dv. And I want dv to be something that I know what the antiderivative of it is. So if I'm starting with secant cubed, it wouldn't make any sense really to say this. It's actually not that we don't know the antiderivative of secant x, because we do now know the antiderivative of secant x. We just know that it's also very complicated, and we want to get something that's a little bit simpler. So although, in theory you could try a choice like this, it's not going to work very well. So instead we're going to write u equals secant x and dv equals secant squared x dx. That's because secant squared x just has a really, really easy antiderivative, which is tangent. And so this is going to be du. The derivative of secant x is just secant x tangent x dx. Okay, so now what I can do is I can write the integral of secant x dx is equal to uv, so that's going to be secant x tangent x, and then minus the integral of v du. So tan x times secant tangent gives me an integral of secant x tangent squared x dx. Okay, so now what I want to do is use one of the identities to rewrite that tangent squared in terms of secant squared. So this is going to equal secant x tangent x minus the integral of secant x secant squared x minus 1 dx. Now maybe you can see where I'm going with this, but this is going to be secant x tangent x minus the integral of secant cubed x dx, and then I'm just combining that minus and I'm multiplying it by that minus 1. So that's going to be plus the integral of, I now have secant x times minus 1 and then the negative of that. So this is going to be plus secant x dx. So now look what I have here. I have on the left side of the equation, I have secant x dx, or sorry, secant cubed x, that was always supposed to be there. I have secant cubed x dx on the left side of the equation, and on the right side I also have another factor of secant cubed x. So what I'm going to do is I'm going to take the secant cubed, move it over to the left side, and that becomes 2 integral of secant cubed x. I want to be very clear about this since I put the wrong power of x on the left. 2 secant cubed x dx is equal to secant x tangent x, and then plus, I still have this secant x on the right side, secant x dx. And then finally I can get the I can just divide the whole equation by 2 to get integral of secant x secant cubed x on the left. That gives me the integral of secant cubed x dx equals 1/2 secant x tangent x plus 1/2 integral of secant x dx. So there we go. That's the integral of secant cubed x rewritten in terms of the integral of secant x. And by the way, a couple of points here. First of all, you should remember from the last video that I do not need a plus c here because this indefinite integral that I'm pointing at already implicitly includes a plus c in it. Second, just note that if I wanted to, since I already know what the antiderivative of secant x is, I could write this in terms of, I could just write this as a closed form without any integral at all, although that was not the question. But I could do this. I could say secant x tangent x plus 1/2 ln secant x plus tangent x. And then finally, for good measure, we put a plus c at the end. We never actually put in a plus c for good measure. It actually always means something. You'd never want to do that, or else you find yourself putting plus c's in definite integrals, which you never really want to do. So that's how you would. This is last point here is not really that's not the answer to the question. It's just a true statement. But if the question is to write the integral of secant cubed in terms of the integral of secant, this would be the answer to that question. This is something that actually we very much like students to be able to do, to be able to do this sort of operation, sometimes with kind of harder versions of it, such as, such as something like the integral of, we might say, computer's going crazy today, you might say something like the integral of, let's say, secant to the 37th of 2x dx, write this in terms of, all right, in terms of the integral of secant 35th 2x dx, because that's the question you always wanted to know in math, is how do you write the antiderivative of secant to the 37th of 2x in terms of the antiderivative of secant to the 35th of 2x. But it's good exercise to be able to go through something like that. So we'll just put a little cloud around that.